Hi, everybody. Welcome back. So, for this entire semester, we've been talking about electricity and we've been talking about magnetism. And I've mentioned a few times how they're actually two forms of the same thing, electromagnetism. We've been able to deal with them separately, but in the last section, we started getting a hint as to how they might actually be related. If I have a changing magnetic field, that's going to produce a current. Well, that means I've got an electric field. If I have a changing electric field, well, then that's going to produce a magnetic field. So, we can get either phenomenon from the other whenever I have these changes. So what we're going to look at today is why that's true. And you're going to see why we know that there is no such thing as a separate electricity and a separate magnetism. They actually are two forms of the same thing. So we've got a lot to do with this. So we're not going to get so much into the calculations with this one. Instead, what I want you to do is get a good conceptual understanding of what's happening. And that's what we're going to focus on in this lecture. All right, let's get started. Okay, to get started here, let's consider that I have two charged particles. So a pair one and a pair two. So two pairs of these. And to start off with, let's think about we have an observer, that's you, who is at rest. You're just sitting there looking at these things. So what kind of force does an observer at rest see between the two electrons in pair one, these two right here? So they're stationary, they're not moving at all. Do they see an electric force, a magnetic force, both forces, or neither force? Pause the video, think about it very carefully, and let's see what you get. Well, they're charged particles. So certainly there is an electric field there, right? There must be some sort of electric force. In fact, in this case, they're repelling each other because they're both negatively charged. Is there a magnetic force? Well, if they're not moving, I cannot have a magnetic force. So I definitely do not have a magnetic force. So in this case, it's the electric force. I'm only going to have an electric force between these. All right, now let's think about pair two. In this case, same two electrons or two similar electrons, but now they're moving with some velocity to the right. You are still stationary, you're the observer. What kinds of forces do you see now? Pause the video and think about it. Well, I have two charged particles. Do I have an electric force? Well, sure, they're still repelling each other. They're still negative. So I've got an electric force. But now those charged particles are moving. So anytime I have moving charges, I must also have a magnetic field. So in this case, I have both forces. I have the electric force simply because they're charged particles, and so they're going to repel each other. But then because they're moving, I must also therefore have a magnetic force. Okay, hopefully that's pretty straightforward. Now, turn to the next page, and let's see what happens if we reverse the situation. So now you are moving. So it's the same situation. So we have those two stationary electrons here, and then we have the pair two is moving off to the right. But now you're moving at exactly the same speed that pair two is moving. All right. So we're looking at this situation here. Don't think about the outside. This is what you see. From your point of view, is pair two moving? No, from your point of view, pair two is just staying there because you're moving right along with it. How about pair one? Well, it's moving in the opposite direction. It's stationary in this lab frame, this reference frame that we've chosen before, but now you're moving this way. So from your point of view, those two electrons are moving off to the left. All right, so given that, first of all, is there an electric field between the two electrons of pair one? Sure, they're still charged particles, so there's going to be an electric force. Is there a magnetic field? Now, this can get a little bit tricky. You may say, well, no, they're not really moving. But remember, your observation point is just as good as anybody else's. You don't know that you're moving. You're standing here on the Earth. You're rotating around on the Earth's surface as the Earth turns, and you don't notice it. From your point of view, you're perfectly stationary, sitting there in your chair watching this video. So from your point of view, those two things are moving. And so, therefore, they must also be expressing a magnetic field. So both an electric force and a magnetic force exist on that pair one. Simply put, got their charges, so they're going to have an electric force. They're moving, so they must also have a magnetic force. Now, how about pair two? Is there an electric force? Sure, they're charged particles, so they're still going to have that electric force. How about a magnetic force? Well, as far as you can tell, they're not moving, and there's no experiment you can do that would show that they're moving. As long as you're moving in a straight line along with these two electrons, there is nothing in the universe you could do to prove that they are not just stationary. And if they're stationary, we cannot have a magnetic field. So therefore, there must only be an electric force right there. But that's crazy, right? The laws of physics can't depend upon whether you're moving or not. So simply by moving, this magnetic field appears and disappears from that. That can't happen. So the only possibility is that the magnetism that we see, this magnetic force, is actually a relativistic effect. It's something that we see only because of things that are moving. And Einstein's theory of special relativity, which we won't get into in this particular course, but Einstein's theory of special relativity says that the way we perceive space and time depends upon whether we're moving. And you may have heard of time dilation and things like that, where if I have an astronaut and he goes off into space at some significant fraction of the speed of light, when he comes back, maybe only a year's passed for him, but 100 years have passed on Earth. Time has actually passed differently. The person on Earth, they say, no, I'm doing just fine. I'm living out my 100 years, right? Whereas the person in the spacecraft says, no, I'm correct. Time, only 1 year has passed. Not only is that just for the clocks, it's also biology. Biologically, they will only be a year older. So it's not some trick of reference frames or anything like that. Time literally moves more slowly. Now, for the most part, you don't see these things in your daily lives. Relativistic effects are really, really small. And you can live practically all your life without worrying about relativistic effects. This is why Newton, when he came up with his model of gravity, he didn't need to have relativistic effects. He didn't think about it. He didn't even know they existed because they were way too small for him to be able to detect. However, if about the only kind of relativistic effect that might affect your daily life is GPS satellites. In order to get your position down to the level of precision that we can do with modern GPS, we have to actually correct for the fact that the spacecraft is not only moving at some fairly high velocity, remember it's in orbit, but also because of the gravitational effects. General relativity actually says that these time dilation effects occur near a gravitational field as well as when you're moving, any kind of acceleration with that. So if you ever saw the movie Interstellar, that's what's happening. Time is passing more slowly because they're near this large gravitational field. Here again, though, it's very, very, very small. And so it's just not something you're going to see. And yet magnetism is something that you can see. I mean, you simply pick up a bar magnet and there it is. But that is strictly because it is a relativistic effect. So the reason why it shows up is that the relativistic effect is significantly smaller. So the magnetism is significantly smaller than the electric force. And if you look at the electric force, there's a huge number of electrons in that wire, maybe 10 to the 22 or so. So if I only had 10 to the 22 electrons and no protons to balance them out, then the force that I would experience as a result of that would be on the order of 10 to the 19 newtons, which would be enough to drag the moon into the earth or something like that. This is a huge amount of force. But almost all of that force is canceled out by the protons. So I'm only seeing, one in however many, 10 to the 20 electrons is going to be unpaired or separated enough that I can actually see this effect. So even though the magnetic force is much smaller, I have 10 to the 20 of them, 10 to the 22 of them in a typical wire from that. And so it may be as much as 0.001 smaller than the electric field, but I have enough of those extras that when I add them up, it's enough that I can actually detect. So interestingly, magnetic fields, magnetism, is one of the only relativistic effects that you can actually observe with your naked eye. It's something that you can observe in your daily experience, but only because I have so many of these electrons or positive charges, if we're working with that, in that one particular object. It doesn't take, even though it's very small, if you multiply by a whole bunch of them, you're going to get something that's actually detectable. So That's what's happening. And that's why they're actually not separable. They are, the magnetism arises simply because it's a relativistic effect from the electricity. We should have come up with a different name for this because really electricity and magnetism, they're the same thing. We call it electromagnetism as though that they were actually still separate, but obviously they're not. So we could call it, pizza if you wanted to, but that's not really going to be very descriptive. And so for tradition, we still talk about electromagnetism. Just remember that if I have an electric field, there's also potentially a magnetic field in there. For some observer, there is a magnetic field. There will be some observer who is moving. Let's say I've got these stationary electrons, and Joe Blow over here, he's actually moving with respect to them. From his point of view, he sees a magnetic field, and it's not a myth, it's real. It's actually there. But you, stationary relative to it, for all you know, you're both moving. You're just moving at the same speed. You're not going to be able to see it. So we know intuitively then, based on this argument, that they're two forms of the same thing. We can't separate them. So the next thing we want to figure out is, okay, how can we describe this linkage mathematically? And that's where Maxwell comes in. I'm going to go ahead and move this page over here so that we can have the, once again, getting those notes so that I can start to write here. So we have learned a number of different equations, and Maxwell took all of these equations for electricity and magnetism and expressed them in a form that showed how they were all linked. And all the things we have studied, everything that we have studied, can be described by 4 equations. Now, these are differential equations. They're fairly complicated. If you want to solve them mathematically, you can do it. You're taking calculus. Once you get into partial differential equations, you can solve these without too much effort. However, what I want to do is I want to show you what each one of Maxwell's equations means conceptually, so that you can see what it's saying and what effect it has on our physical world. Then later on if you take a full electricity and magnetism class, E&M class, then you'll say, oh, okay, I'm solving this for a particular value, for a particular electric field in this case, or whatever, but I intuitively understand physically what's going on. Okay, so a couple of things that we're going to need with this. So the first equation that we talked about was how to get the electric field. And so if I have a charge, let's say that I've got some positive charge right here, what does the electric field look like? Well, the electric field lines spread out in all directions, just like this. Okay, so that's my electric field right there. We say that it's diverging out from there because the field lines are continually getting farther and farther apart. So it's diverging. Now, we know Gauss's law. Gauss's law, we said, was the path integral of the electric field dotted into some surface volume must be equal to, and we originally did this as 4 pi kq, where q is that charge that was enclosed. But remember, we introduced this operator. We could say that k is also 4 pi epsilon naught, where epsilon naught is the permittivity of free space. That's one of the fundamental constants of the universe. So that's really what we want to use. Rather than this k that was originally defined historically, turns out that this is set by the universe. So let's go ahead and express it like that. And we've done this before. And we found that we got simply q over epsilon naught. All right. Now, we can introduce a new operator, this del operator, and it's a vector. And that is going to be equal to, it's a vector that's the partial of whatever field I have. We're not going to put in our field because it applies to anything. In Cartesian coordinates, it would have a coordinate partial x, partial y, partial z. And these are the 3 coordinates. Now I could do it in spherical coordinates, and I've got r, theta, and phi, all this sort of thing. We'll stay with Cartesian coordinates for now. So if I take this vector and I dot it into another vector, like the electric field, something like this, then remember, if I take the dot product, then I'm only going to get the part that is parallel that are in the same direction here are the only parts that's going to contribute. And so this is going to give me partial E partial X plus partial E partial Y plus partial E partial Z. And effectively then, this is going to end up being my X component, how it changes in X, how it changes in Y, and how it changes in Z. Notice that this is a dot product. Will that give me a scalar or that give me a vector? It's going to give me a scalar. And it works out that this is going to give us rho, a charge density, divided by epsilon naught. And the only reason it's a charge density is because now because I'm working in X, Y, and Z, I don't necessarily have to have a point charge. I could have something that's distributed throughout. Other than that, there's not really any difference. If I do have a point charge, well, then this is just going to become Q. So this is just a little more general way of doing this. This operator here, this del dot, is called the divergence operator. And so what this does is it describes how the electric field changes in space. So if del dot E is positive, so let's say it's greater than 0, which if I have a positive charge density, if I have like my positive here, then what that means is that the field lines are spreading outward. They are diverging outward. So since del dot E for a positive charge is going to be positive rho over epsilon naught, then that tells me that my lines are moving outward. On the other hand, if this is a negative, if the divergence of E is less than 0, same thing, it just means they're diverging towards the source. So it's diverging towards this rho, this charge density from here. So this then, all this equation says is, hey, field lines move out from my charges. In the case of a point charge, the field lines diverge outward. It has a positive divergence for positive charges and a negative divergence for negative charges. Negative divergence just means they come together. So this is the first of our Maxwell's equations, and it's simply Gauss's law. This is just another way of writing Gauss's law. It gives you the exact same thing, but now I'm not restricted to using point charges. And so I can take any charge density. I can take our wires, we can take our capacitors, everything that we've done, and I can see how it changes in X, Y, and Z. And that's worth doing. You know, in fact, we had a case where the case of my capacitor, if you remember, when I had a charge plate, then the electric field actually only depended on this, we'll call this the X direction. And so the only part that survived was the partial E partial X. And that would be equal to my charge density over this. And when we integrate that, then you're going to see that we got something very similar to what we got before. So that's going to give me rho epsilon naught, which are going to be constants here. And so my electric field then depends only upon the charge density, this constant, and then the distance that I am away, how far in this delta X I am. Exactly what we found before. So Gauss's law applies to any situation, but written in this form, we can immediately see, since this is the divergence, we can immediately see that that means the field lines are spreading out. They're diverging from each other. That's the important thing that I want you to remember for this. Okay, so here's our first one. We'll go ahead and keep up with them up here. So this is Gauss's law, and that simply says the divergence of the electric field, this is a dot product, the divergence of the electric field is positive for positive charges. That's it. That's what it's saying. And of course, by analogy, it means it's negative for negative charges. All right, so we'll go ahead and erase this so we can keep everything on the same page. All right, so the next thing that we talked about was Gauss's law for magnetism. And so we'll go ahead and label that here. That's pretty poorly written, Gauss's law. This is Gauss's law for electricity. And so we'll do Gauss's law for magnetism, which was B. And this, remember, was not terribly useful to us because we found that it was, if I had B dotted into dA, what was that equal to? Do you remember? Well, it was 0. So the flux through any closed surface is going to be 0. So what that tells me then is, if I use an analogy here, remember my original form that I had was this was equal to Q over epsilon naught. Remember, I have to go to density simply because I'm spread out amongst a field rather than a point source. So this then, Gauss's law for magnetism then, can be written this way. Del dot B must equal 0. So del dot B, remember, is the divergence. It's showing us how those field lines are spreading out. Gauss's law for magnetism tells us there is no divergence in the magnetic field. So the field lines I can't have a north pole and just have it spread out and never come back together. So literally what this says is there's no such thing as a magnetic monopole, which we proved before from this. And so any kind of charge distribution, then I must have nothing but closed loops. So if this is my magnet here, I can't have it moving off into infinity. It has to be some sort of a closed loop for this. All of my magnetic field lines must be closed loops. If they were not, then this would not be 0. It would show that I would have some kind of divergence if it doesn't close. Well, it is 0. So therefore, I must only have closed loops. And also that tells us that there's no such thing as a magnetic monopole. All right. So that one was pretty straightforward. The third one that we've talked about is Faraday's law. And remember that Faraday's law tells us about the voltage that we get if we have a changing magnetic field. And so we got this induced voltage, and Lenz's law said that had to be negative, times the change in the flux, the magnetic flux with time. That was Faraday's law as we defined it. Now, this was also going to be equal to my path integral around a loop around my electric charge. So remember, if I had that current carrying wire, then I could go around that current, around that electric field that was being produced. And that would enable me then to figure out what was my magnetic field that was changing through there. So the other way that I can write this then is with a new operator called the curl. And it still uses that del. So, but now it's del cross E. And what Gauss's law says is that del cross E, this is called the curl. And so what that shows me is how the magnetic field lines curl around that electric field, around the electric field curls around that magnetic field, and vice versa. And we said that, okay, that then tells me that my magnetic field must be changing in time. And this is a vector, which is good because my curl, my cross product here, is also going to give me a vector. Now there is a constant of integration, which for now we'll just call 1 over c that's in there. And if I take this function and I do the integral, then this is what I will get out of it. Again, we're not terribly interested in doing the math here. We want to be able to interpret what this says. What this says is that the magnetic field must curl around my changing electric field. So similarly, if I have a magnetic field that is changing in space and changing in time, then I'm also going to generate a current. And we know that current is also going to be in my loop. So, and the example we had was, here was my loop and here was my magnetic field. Here was my magnet. So as my magnetic field changed in time, that generated a current in this loop from that. So this is another way, this is an equivalent way to write Faraday's law from this. We're going to talk about what each of these mean. We're going to remind ourselves what each of these mean in summary in just a second. So we'll copy it down. Whoops. We'll copy it down over here. And that's a vector dt. Okay. So quick summary then. So far, Gauss's law says that since it's a divergence, the electric field diverges away from the charge. So the electric field diverges away from the charge. And we're using rho here because I might not have a point charge. But if I have a point charge, then it's just going to be Q. Gauss's law for magnetism says the divergence of the magnetic field is zero. It never, ever opens outward, so I never have any magnetic monopoles. There's no way for that to happen. If you could ever find a magnetic monopole, then that means basically everything we know about physics is wrong. And so that would be a big deal. Faraday's law says if I have a changing magnetic field, so if the flux is changing, the magnetic field is changing with time, then I'm going to generate an electric field. I'm going to generate this current that's produced, and vice versa. Okay. So the last of Maxwell's equations is simply Ampere's law. Now, when we defined Ampere's law, we used this to find the magnetic field, and we said that it was B dot L instead of E dot L. And we said that that was the permeability of free space times the current that was enclosed. All right, and so that was over a loop. Now, here again, what this says is that so this says the electric field curls around that B. Well, this says that B, this allowed us to calculate the electric field that was being produced, the voltage. Remember, voltage is an electric field that was being produced by that changing magnetic field. This tells us that I must have some sort of a current. And so when this was done, we're going to put our constant of integration back in here so that it has the same form as this. But now it's going to be the change in the electric field with time. So let's look at what this says. What this says is that, that shouldn't be a cross, a dot, that should be a cross. Sorry. There we go. So what this says is if I have a changing magnetic field, Faraday's law says then the electric field that is produced will curl around that magnetic field. In Ampere's law, so here in Faraday's law, I was trying to find that electric field. In Ampere's law, I'm trying to find the magnetic field. So here I have a changing electric field. And when that electric field changes, then I'm going to generate a magnetic field. All right. So the only real innovation, so far, none of this is new to Maxwell. The only real innovation is that he realized that, and you probably realized this too, that if I have a magnetic field that's changing, that's also going to produce a current. So here I have a changing electric field. That's going to produce a magnetic field. If that magnetic field is also changing, then I must also have a current. And so that worked out to be 4 pi c, and then he used the current density J. Again, we're going to stay with these densities so that I don't have to worry about point charges and things like that. So J is the density of current in the wire, for example, that's producing that. So this is now called the Ampere-Maxwell law. And all it is Ampere's law, which is this part, plus this extra current term. And this extra current term is called a displacement current. And if you think about it, that's actually kind of obvious, isn't it? It should be there from the beginning. But Maxwell was the first person to actually write that in there. If I have a changing magnetic field, then I must also have produced a current in there at that time. So these 4 equations then describe everything that we've talked about in this course. Everything can be derived from these equations. And if you take a full electricity magnetism course, a full E&M course, you'll probably start with these equations. And then from that, then you can derive, okay, I want to figure out here, I've got this charge density. What's the electric field from it? Well, okay, I'm going to go to Gauss's law, but I'm going to go to the differential form of Gauss's law like we have here. Because it might be spread out. It's not going to be just point charges or wires or things like that we've been talking about, the simpler cases. All right. So this is very important. And the reason why Maxwell got so much fame and glory for it is because it's nice and compact. It's a simple, elegant way to explain everything that's happening with electromagnetism. Okay, so the question then becomes, why were the constants of integration chosen to be what they are? And so right now we haven't tried to solve for those. We know that if something is related to the magnetic field, it must be related to this constant, mu zero, this permeability of free space. Similarly, if something is related to the electric field, we found that the constant of integration we defined to be the permittivity of free space. So it's pretty easy to see that anytime I'm working with an electric field, that constant of integration has to involve one or both of these. However, remember that, so for example, when we look at Faraday's law, we have both of them. So my constant of integration is going to end up having to have both of these involved in it. And we can work out what that is by simply combining them. So let's do that. Let's suppose that I have an oscillating electromagnetic field. So I have an electromagnetic field that's changing in space and time. And we could get this from the LRC circuit that we talked about last time, from an inductor. So I have this wave, and we'll say that this is time and this is the electric field. Now, don't forget that the magnetic field is also changing in time. And if I had my magnetic field, it's also going to be like this. However, this is also propagating through space. We talked about how I could have a transmitter and I could have a receiver. So if I wanted to try to do this in both space and time, okay, well, that's going to get a little bit confusing, but let's try drawing it in 3D like this. Then my electric field, so now this is space. Let's just get rid of this bottom one here. I don't think I can draw without it. So this is space, and this is my electric field. So it's also oscillating like this as it moves through space. Now, the time it takes to reach here is related to the frequency of that wave. The magnetic field, B, let's do that in a different color, is also going to oscillate, but it's going to be at a right angle like this. Okay, so if I were going to draw this from the side, if I'm looking down my field here, my magnetic field is going to go back and forth like this, whereas my electric field is going to go back and forth like this. So I'm going to get that 90-degree plus mark. And that makes sense. We know that they have to be at 90 degrees angle to each other because of the cross product from that. Okay, so I've got this wave then, this electromagnetic field that is changing in space and time. So what we can do is we can combine both the Faraday law and the Maxwell Ampere law. And that's what I've started to show you here. We know that the magnetic field depends upon this quantity, this del cross E, the curl of E. And we would have to solve the differential equation to work out exactly how, and we're not going to do that. But hopefully you should be able to see that I can plug that in here because this is B. And the left side of my equation must look something like this. Exactly what it's equal to is going to depend upon how I solve this. But you see that I have this constant 1 over C, and I see that E is changing in time. Well, I also know that E is changing in time as a result from this previous equation. So this is kind of like a second derivative, and I'm also going to get a second derivative here. But now I've got 2 of those constants of integration, and it's going to give me something like this. Again, the details working this out is a lot more than we're going to have time to do. And I know you might say, well, okay, if you say so, Dr. K. But really what I just want you to see is that I've got 2 derivatives. I've got one time derivative here. I've got a time derivative here. And then this is a space derivative. It's that partial x, partial y. So I've got a space derivative here and a space derivative here. So on my left-hand side then, I've got my space derivatives. And on my right-hand side, I've got my 2 time derivatives. That's where they come from. So if I were going to combine these then, I would write this way. Del cross E is written as del squared E. Like that. And this, of course, then is just going to be my second derivative with respect to time from that. So this is my oscillating electromagnetic field. So this equation describes how that RLC circuit's electromagnetic wave is going to propagate through space. And we do know that it is a wave. When you start taking your ordinary differential equations, your partial differential equations classes, you get into a second order partial differential equation, which is what this is. And what you'll find then is that this this equation has a very well-known form. The solution of this has a very well-known form, and the solution is a wave. And so this gives me an electric field that changes in both space and time, and it's going to have the general form of some constant, sine, and then the space part has a constant in front of it, kx, minus this constant c, remember goes with t, goes with time. And then I might also have another portion of it with the positives. So sine of kx plus ct. That's the most general form of a wave. And what would be a good exercise for you would be to take this solution and plug it in to this equation. Right now, we're assuming that it's only propagating in x. So remember that del then in this case would just be partial x. So take this entire expression, take the derivative with respect to x twice, and write what you get down here. Then take this expression, take the derivative with respect to time twice, and you're going to see that you're going to get the same thing, that they're equal to each other. And so that's how you can prove that this is. But when you get into calculus, you're going to see that this equation is called the wave equation. And the solution is always going to be this sine, this oscillating sine function that moves throughout. All right. The interesting thing, though, is the constant here. Remember, we've got one of the constants that depends upon time, that depends on the magnetic field, and one of them that depends upon the electric field. So the constant works out to be c squared ends up being 1 over mu 0 epsilon naught. One from the magnetic field, one from the electric field. And if you don't like that, remember we actually have a 1 over c squared here. That's going to equal that. So my constant c then must be equal to 1 over the square root of mu 0 epsilon naught. Okay, so this constant, this c, represents the speed of that wave as it propagates. And this is true for any wave. It's true for sound waves, it's true for water waves, it's true for everything. Whatever that constant c is in front of the time tells me the speed at which it's propagating. The k, by the way, gives me an idea of the wavelength. It's called a wave number, but it gives me an idea of how long the waves are. But the c tells me how fast things are changing, or how fast it's propagating. Well, notice that both of these constants are constants of the universe. They never change. So what we want you to do in microtask 3 or microtask 2 is figure out, what is this speed? Okay, well, you know that mu naught is going to be 4 pi times 10 to the minus 7, and you know that epsilon naught is going to be 8.85. Let's go ahead and take one extra term here. So it's 8.854 times 10 to the 12th. So pause the video, multiply those out, take the square root and invert it, and tell me what you get. Pause the video, really important. Well, when you work that out, and if we're careful with keeping all of our units, what you're going to find is that you get C is 2.998. Whoops, I got one extra 9 in there, sorry. 2.998, my pen to cooperate, times 10 to the 8th meters per second. That is the speed of that oscillating electromagnetic wave. Well, we discovered that that was radio in the case of our RLC circuit, but you may recognize this as the speed of light. All light is nothing more than an oscillating electromagnetic wave. And because the constant here, the propagation speed, is determined by constants of the universe, it's the same everywhere. It never changes. So the speed of light is an absolute constant of the universe. It doesn't matter who you are. It doesn't matter what you're doing. It doesn't matter how you're moving through space. So Einstein's special relativity comes out of the assumption that everybody measures the same value for the speed of light. So for example, if let's say you're in a car, right? And this is my funky looking car. It's a convertible. And we're driving this way. If you're moving, let's say at 60 miles per hour, and you turn on your headlights, so that that beam moves out through here. That beam still moves at the speed of light. 998 times 10 to the 8th meters per second. It does not move at c plus v. Well, that seems a little bit crazy because the only way that's possible is, it turns out, if space and time are two forms of the same thing. And this gets into special relativity and the fact that time must be moving more slowly because everybody measures that same value for c. And Einstein realized that because it depended only upon these two constants of the universe. And the reason why we use the value c for the speed of light is not because, oh, constant. No, we've got lots of constants. It just happens to be the constant of integration in Maxwell's equations. That's all. When he wrote it in his original papers, he just said, oh yeah, there's some constant of integration, 1 over c, and by the way, that works out to be the speed of the wave. But when you do the math, it works out that that has to be the same for everybody because it doesn't depend upon anything else. Okay, so the last thing that we want to talk about then is this idea of this propagation of the wave. And we said that, okay, they're all moving at the same speed. And we said that this k value was related to the wavelength, the length between our peaks of the wave. Let me erase some of this here so that we've got some space to work, because I want to keep Maxwell's equations up there in case we need them. So if I have a wave that's propagating through space like this, and let's look at the electric field. It doesn't matter. We could talk about the magnetic field. It would look the same. It's just going to be, in space, it's going to be moving at some angle. The distance between this, so let's move through space for now. If I'm moving through space, the distance between this is called the wavelength. And we use a lowercase Greek letter lambda. A lot of my students just call it chicken foot because it looks like a chicken foot. But this is a distance, and it's measured in meters. For most light waves, it's on the order of nanometers. So it's going to be 10 to the minus 9 meters between each one of these peaks here that you see. For radio waves, it could be anywhere. For FM radio, it's on the order of the size of a mountain. For AM radio, it's on the order of the size of the United States. For very high frequencies, for very rapidly rotating, so this oscillating fields, this might be an X-ray, and so that could be even smaller than nanometers. And the more of those waves that I have in one space, then obviously the shorter that they're going to be. So there is a relationship then between the frequency, the number of waves I get each second, and the wavelength. So let's look at two waves here. So here I've got wave A, and here I've got wave B. And we'll look at the electric field for both of them. And let's say that wave B looks like this. And so here's my wavelength. By the way, when you draw a wavelength, always draw it from peak to peak. It's not from top to bottom from that. That's actually only half a wavelength from there. All right, so this is the wavelength for that one. Which one has the longer wavelength, wave A or wave B? Well, wave B, obviously. Now, which one has the higher frequency? The frequency is the number of peaks each second. So let's say that I'm sitting here, that I'm right here, and I'm watching these waves come into me. So I'm receiving them. And if I give a beep every time I receive one of these peaks, then I'm going to get more beeps per second with wave A than I am with wave B. That's only true because they're moving at the same speed. If wave B were moving much, much, much faster, well, then even though it's got a long wavelength, they would come at a faster rate. And so I would have a faster wave, I would have a faster frequency for that. But this is light. All light moves at the same speed. So which one of these then has the higher frequency, A or B? A must have the higher frequency. So A has the highest frequency, but it has the shortest wavelength. Are they directly proportional or are they inversely proportional? They're going to be inversely proportional. And so my frequency then must be inversely proportional to the wavelength. And the constant of proportionality in this case is the velocity, the speed of light. This holds for any wave. If it's sound, then instead of the speed of light, it's going to be the speed of sound from there. But this is an equation worth remembering because it allows you to translate between the frequency and the wavelength. Radio stations, for example, let's say you've got a radio station, an FM station called 96.9. That's 96.9 megahertz, 96.9 million cycles per second. Well, since you know the speed of light, because it's radio, it's just light, then you could figure out the length of the waves by plugging it into this equation. So that would be a worthwhile skill to have. So what Einstein discovered, but Einstein and Max Planck discovered when they started working with quantum mechanics, is they realized that there's a relationship between the energy of the wave and the frequency. If you think about it, that kind of makes sense. If they're moving at the same speed, right, I'm going to get, if I have no wave, if it's just flat, well, I don't have any energy in that. If I have a continuous peak up here, well, then I've got a lot of energy with that. So here, I'm going to get energy whenever one of these peaks comes in. This wave, wave A, I'm getting more peaks per second, therefore I must be getting more energy. So would you say that the energy is directly proportional to the frequency or inversely proportional? This is microtest 3. Well, they must be directly proportional, because the higher the frequency, the more energy I'm going to get, because I'm going to get more of these peaks coming in. So we know that E, and this is the energy, and so don't get confused. This is a scalar. This is not the electric field. We've run out of symbols. We know that it is proportional to the frequency. What Planck figured out was, and Einstein figured out, was that constant of proportionality was the Planck constant, H, which has, if you look in your book, we've got that down here, it's 6.626 times 10 to the minus 34, and then the units have to be joules per hertz, because frequency is measured in hertz, and then energy is measured in joules. So this is a new constant, and this is called Planck's constant from here. And so that allows us to determine the energy of any kind of light. If all I have is the wavelength, well, that's fine. I can convert it to frequency and then convert it to energy after that. So by putting all of this together, then I can describe any kind of oscillating electromagnetic field, any kind of light. What we're going to be talking about from here on out for the rest of the semester then is, how does this electromagnetic wave, light, how does it behave? Right now, we've already discovered two of its fundamental properties: the relationship between its wavelength and its frequency, and the relationship between its energy and its frequency. All right, so what we've learned up to this point is, if I have an electric field and therefore a magnetic field that changes in space and time, it's going to propagate as a wave, and we call that wave light. So this ends the formal part of the electricity and magnetism section of the course. We're going to be talking about light from here on out, but don't lose sight of the fact that when I'm dealing with light, I am dealing with an electromagnetic field. For most of history, we didn't realize that. We thought that light was something completely separate. And so our initial study of light was always done with this approximation of, well, I've got these light particles coming in, or maybe I have some sort of light wave coming in. But we didn't understand what it was. You now understand what is causing that wave, and it's simply an electromagnetic field that's changing in time from that. So the study of light is called optics. So picking up with our next video, then our next lecture, we're going to start looking at optics in detail and figuring out how we can study light and utilize it to learn all kinds of new things about the world around us. We'll see you then.